Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to the course on Advanced Transition Metal Organometallic Chemistry. Continuing with our discussion on organometallic catalysis reaction, today we are going to be talking about the largest scale industrial process under homogeneous catalysis. This application of organometallic chemistry is so huge, about 7 million tons per annum of the product is produced using this particular reaction, and this reaction is none other than hydroformylation reaction discovered almost a century back by Otto Roelen. So, today we are going to be talking about this reaction which is the largest scale industrial process under homogeneous catalysis. We have, in this context, let me note that we have also looked at the longest application of industrial scale organometallic catalysis, and that was Walker oxidation using ethylene to produce acetaldehyde. So, that has been in place for more than a century now, and this reaction, which is hydroformylation, is the greatest application of organometallic catalysis, by which about 7 million tons of products are produced annually using this reaction in industry. This hydroformylation process is also known as OXO process, and there are two similarities that exist between this the largest scale industrial process, which is hydroformylation, and the longest known industrial process under homogeneous catalysis, which is Walker oxidation. The first similarity being that both used ethylene or olefin as a substrates. So, both of these reaction, the longest known as the largest scale, uses olefin as a substrate for conversion to the product which is an aldehyde. Now, in both the cases too, in Walker oxidation, the longest known homogeneous catalysis process, as well as this hydroformylation reaction, the largest scale industrial process under homogeneous catalysis, the product so formed also is an aldehyde. So, there is a lot of excitement about these two reactions, and we have covered in details the Walker oxidation, and in today's lecture I am going to be talking about this largest scale industrial process under homogeneous catalysis reaction, which is this hydroformylation reaction or the OXO synthesis. So, the amount of alcohol produced by this method is about 7 into 10 to the power 6 tons per annum, which is a large amount of chemicals produced by this, and hydroformylation is the largest scale industrial process of homogeneous catalysis. The reaction was first observed and patented by Otto Roelen in 1938 using a heterogeneous cobalt catalyst. and the actual catalyst is a cobalt hydride complex which is formed from the carbonylation of cobalt oxide with hydrogen and CO. Is formed from reductive carbonylation of cobalt oxide with hydrogen and carbon monoxide. So, in fact, this hydroformylation is addition of hydrogen and CO across a double bond and is aptly given by this equation. And the reaction is given by CH2 CH2 CO plus H2. The active catalyst is HCO4. Temperature range is about 90 to 250 degrees centigrade, about 100 to 400 bar, giving CH3 CH2 CHO. Now, the relative reactivity of alkenes in this transformation is given as follows. Is terminal alkenes to internal alkenes more reactive than sterically hindered terminal alkenes, more reactive than sterically hindered internal alkenes, more reactive than sterically further more sterically hindered internal alkenes. So, reactivity decreases with increase in sterics. So, this is reactivity decreases with sterics, steric increase. So, this is an important observation which shows that terminal alkenes are more reactive than the internal ones, because obvious reasons that this is more sterically demanding than this, and then internal alkenes are more reactive than sterically hindered terminal alkenes, and sterically hindered terminal alkenes are more reactive than sterically hindered internal alkenes, and this goes on. So, the reactivity decreases with sterics. Now, before I proceed to talk about the catalytic mechanism for this hydroformylation reaction, I must dwell a little bit on this coincidental correlation that I had just noted at the beginning of the class about the two industrial processes. One is and this hydroformylation reaction, which is by far the largest scale industrial process under homogeneous catalysis, and also this Walker oxidation reaction, which is the longest known industrial process under homogeneous catalysis. The similarity that I had drawn is the substrate and the product for these two industrial process. The longest known industrial process under homogeneous catalysis is Walker oxidation, and the largest scale industrial process under homogeneous catalysis is hydroformylation. For them, the reactants which is ethylene and the product which is aldehyde are the same. So, one can see and the other point that I want to make is that the aldehyde as a product is very important starting intermediate to accessing many other many other compounds, because aldehydes are amenable to various transformation of various functionalities, because they can be converted to different targets using organic manipulations. So, these two processes not only highlights the importance of aldehyde as a target material to be produced in the industrial scale, but also this shows that there can be multiple ways of accessing aldehyde from ethylene through oxo process or through hydroformylation reaction, and each of them can be equally important and be practiced in industry. So, these I believe is a very important correlation that one should keep in mind while taking a look at hydroformylation reaction and Walker reaction. So, with this let me just talk about the various products produced by hydroformylation reaction. Actually, it sets out a set of reactions and C3 to C15 aldehydes are produced by respective olefins by oxo process, and they can be further converted to amines, carboxylic acids, alcohols, and that sort of once again highlights the importance of aldehyde from industrial perspective for accessing other important compounds, and hence from that standpoint these two processes gives direct access to producing aldehydes in large scale, and that is why they have been extremely successful and popular in the industrial world. So, C3 and C15 aldehydes are produced from the respective olefins by oxo process, which can be further converted to amines, carboxylic acid, alcohols, and etc. So, from industrial point of view, as I said that aldehydes are extremely important, but they can be converted to whole range of other chemicals like amines, carboxylic acid, aldehydes, and this for hydroformylation provides a useful method for synthesizing these aldehydes from C3 to C15 fragments, and this is illustrated by this sequence of reaction: propane plus CO plus H2 in presence of a catalyst gives propanaldehyde that can be terminal, or the aldehyde can form at the internal carbon, giving a branched aldehyde. So, these 2 can be further reduced to corresponding alcohol in presence of hydrogen, and in that case one would obtain these two alcohols. In presence of base, the aldehyde can undergo, these two aldehyde can undergo condensation to give the following product, that would eliminate water to give this, and that in presence of hydrogen would produce the corresponding alcohol. So, what it says that these hydroformylation reaction sets out several sequences of reaction that can eventually be used or leads to formation of different products. Now, hydroformylation of terminal alkenes are industrially important because they and one such usage is in production of 1,4-butanediol, which is a very important intermediate in synthesis of THF, the ethyl 2-ethyl hexanol and higher terminal alcohols. So, hydroformylation of terminal alkane is industrially important and that is given by one COH2 and rhodium catalyst, and second is dihydrogen to give Raney nickel reduction to produce this 1,4-butanediol, and this butanediol is used in the important intermediate used in the synthesis of THF, tetrahydrofuran, 2-ethyl hexanol and higher terminal alcohols. So, one can see the impact of these hydroformylation reactions for producing intermediates which are industrially important and for several reasons, and this can be done by taking terminal alkenes and then converting them to aldehyde and then subsequently reducing with hydrogen and Raney nickel to give this butanediol. Conjugated dienes has the problem of isomerization during hydroformylation reaction, and this is governed by energetics of the diene itself. The conjugated dienes has the problem of isomerization during hydroformylation. And this is primarily due to the very close energetics of the conjugated dienes and their isomers, and that is probably what governs this isomerization process during hydroformylation. Now, let us take a look at the mechanism of hydroformylation. So, the active catalyst is cobalt hydride tetracarbonyl, which loses a carbon monoxide CO to give the active species HCO, CO3. So, then comes this olefin coordination step H2C CHR. This is the coordination step. So, that coordinates and forms HCO, CO3, H2C, CHR, and then is the insertion of this olefin into the cobalt hydride bond to give the cobalt alkyl complex R CH2 CH2 CO CO3. So, this step is the insertion step. Then as the compound due to this insertion of olefin into cobalt hydride bond becomes coordinatively unsaturated, and that vacant site is occupied by the CO, which was liberated over here to give R CH2 CH2 CO CO4, and this is the coordination step again, but this time around this is coordination of CO. Subsequent to the CO coordination, is migration of the coordinated CO into the metal alkyl bond R CH2 CH2 CO CO CO3. So, this is migration of the coordinated CO. So, this again the coordination insertion into the alkyl bond. So, now so far if I look at this hydroformylation process, we had seen that there are two sequences of coordination insertion happening over here. The first coordination insertion happened with respect to the olefin. The olefin got coordinated and then inserted into a cobalt hydride bond, and then the subsequent coordination insertion occurred with respect to CO. The CO got coordinated and then inserted into the cobalt alkyl bond. So, there are two steps of coordination insertion occurring over here, and then one with carbon monoxide the second one is with carbon monoxide, the first one is with alkene, and then the reaction of hydrogen is the oxidative addition giving R CH2 CH2 CO cobalt dihydride CO3. So, this is a cobalt oxidative addition reaction occurring over here, in which the hydrogen activation occurs, and then finally the reactive elimination giving rise to the product R CH2 CH2 CHO. So, this is the reactive elimination step. So, with this the cobalt hydride tricarbonyl is regenerated. So, this sort of closes the loop and finishes this catalytic cycle of this very important reaction, which is the biggest largest scale industrial process known so far. So, this reaction the catalytic cycle with cobalt hydride consists of 6 elementary steps. There are 2 sequences of coordination insertion occurring. The first one is occurring with the olefin and olefin coordination versus olefin insertion into a cobalt hydride bond to give the cobalt alkyl moiety, and after the cobalt alkyl moiety is formed, the second sequences of coordination insertion is seen to occur, and this second insertion is occurring with respect to carbon monoxide. So, carbon monoxide coordinates and then inserts into cobalt alkyl to give the cobalt acyl bond RCH2COCH3, and after this oxidative addition of dihydrogen is seen to occur to give a cobalt dihydride complex, which eventually will reductively eliminate to give the required hydroformylated product along with the regeneration of the catalyst. So, and subsequent to this the cobalt catalyst, there is an improvement on this, and people have come up with there is a rhodium catalyst which is right now be commercially used, even though rhodium is very expensive, but the catalyst is so active that that its high turnover number, extremely high turnover number makes up for its expensive metal. Okay, so with that let me just conclude today's lecture on hydroformylation reaction and recapitulate what we had discussed in today's talk. As we started off on hydroformylation reaction, bearing an analogy with respect to the Walker process, which is the oxidation of ethylene to give acetaldehyde, and what we had noted that both the process of hydroformylation forming olefins to aldehydes and the Walker process converting ethylene to acetaldehyde, for both of the process the starting materials are same, which are olefins, and the product are also the same, which is aldehydes. We have also noted that these aldehydes are important intermediates which can further be converted to other targets, and that is why there is a huge demand for large scale synthesis of aldehyde. We had observed that this hydroformylation, also known as OXO process, was discovered around 1938 by Rolin and subsequently patented and then followed up. The catalytic cycle of hydroformylation reaction involved a formation of cobalt hydride tetracarbonyl species, which then underwent a sequence of coordination insertion with the reacting substrate, which is an olefin, to give a cobalt alkyl complex, and that complex then again underwent a sequence of coordination insertion to give a cobalt acyl complex using with carbon monoxide, and finally the addition of hydrogen to give oxidative addition followed by reactive elimination would close the loop and give the desired product aldehyde along with the formation of cobalt hydride species. So, with this I conclude today's lecture on hydroformylation formylation reaction, and formally all the topics that has been covered in this course is covered with this discussion on hydroformylation reaction. I sincerely thank you for patiently hearing me in this lecture, and I look forward to the last lecture which is of the course, which is in the next lecture, which would be the next lecture in which I would give a summary of all the topics that has been discussed as a part of this course. So, with that thank you and goodbye.